We are going to see the new chapter in chemistry, that is Unit 14, Biomolecules. Now, examples for biomolecules are carbohydrates, proteins, nucleic acids, etc. So, in this chapter, you will learn about carbohydrates, proteins and nucleic acids in detail. First, let's see about carbohydrates. Carbohydrates. Now, carbohydrates examples are sugar, glucose, starch, fructose, etc. And the carbohydrates have the general formula CHH2O Y times, and we can consider this carbohydrate as hydrates of carbon. So, carbohydrates can be considered as hydrates of carbon. For example, we know the molecular formula of glucose is C6H12O6, and this formula fits in the general formula for carbohydrate, that is C6H2O times, and you can write it as the general formula, that is C6H2O 6 times. So, glucose can be considered as a carbohydrate because its formula fits in the general formula for carbohydrates. But all the compounds which fit into this formula may not be considered as a carbohydrate. For example, acetic acid. You know the formula of acetic acid is CH3COOH. Now this formula fits in the general formula of carbohydrate, and we can write this acetic acid as C2H2O twice. That is, this is CH3COOH, C2H2O twice. But we know acetic acid is not a carbohydrate. So the compounds which fit into this formula, there are exceptions which are not considered as carbohydrate. Now, there is another carbohydrate, that is rhamnose. Rhamnose. And the formula of rhamnose is, molecular formula is C6H12O5. And we know this molecular formula does not fit in the general formula of carbohydrate, that is CXH2O Y times. But rhamnose is a carbohydrate. So there are exceptions also for this rule. Now, these carbohydrates, they contain a specific functional group, and usually it is either aldehyde or ketone group that is present in a carbohydrate. Now, we are going to see a definition for carbohydrate. The definition is, carbohydrates may be defined as optically active. Optically active polyhydroxy aldehyde or ketone, or the compounds which produce such units on hydrolysis. So this is the definition of carbohydrate. They are optically active. Optically active means we know that they can be dextrorotatory or levorotatory, means they will have a plus or minus sign. Optically active polyhydroxy. Hydroxy group is OH group. Poly means 3 or more than 3. Polyhydroxy, they contain the functional group aldehyde or ketone, or the compounds which produce such units on hydrolysis, or if the compound is capable of producing such optically active polyhydroxy aldehyde or ketones on hydrolysis, they can be called as a carbohydrate. Now, we know that the carbohydrates, some of them are sweet in taste, and they can also be called as sugars. And you know the sugar present in milk is lactose, and the sugar that we commonly use at home is sucrose. Then carbohydrates can also be called as saccharides. Saccharides. They can also be named by saccharides. Now next let us see the classification of carbohydrates. Classification of carbohydrates. Now, carbohydrates can be classified on the basis of their behavior on hydrolysis. So, the classification is based on the hydrolysis. Now, they are divided into three groups. The first type of carbohydrate is monosaccharides. Monosaccharides. Now, what are monosaccharides? A carbohydrate which cannot be hydrolyzed further to give simpler unit of polyhydroxy, aldehyde or ketone is called a monosaccharide. So, monosaccharides means they cannot be hydrolyzed further, they are monosaccharides. And about 20 monosaccharides are known to occur in nature. An example for monosaccharide is glucose, then fructose, ribose. These are three examples for a monosaccharides: glucose, fructose, ribose. They cannot be hydrolyzed further. Now the second type of carbohydrate is oligosaccharides. Oligosaccharides. Now, what are oligosaccharides? Carbohydrates that yield 2 to 10 monosaccharide units on hydrolysis are called oligosaccharides. So, oligosaccharides means these carbohydrates when hydrolyzed we get 2 to 10 monosaccharides. They are oligosaccharides. Now, we can again classify these oligosaccharides as disaccharides, trisaccharides, tetrasaccharides, etc. depending upon the number of monosaccharides they provide on hydrolysis. So, amongst these we have the most common as disaccharides. So, here we have to study about disaccharides also. And what do you mean by disaccharides? Disaccharides means carbohydrates which give 2 monosaccharides on hydrolysis. We get 2 monosaccharides on hydrolysis. They are disaccharides. And the 2 monosaccharides that is obtained, it can be of the same or they can be different also. Okay, for example, this sucrose. Sucrose on hydrolysis, you get glucose and fructose. And the formula of sucrose is C12H22O11, which on hydrolysis, the glucose formula is C6H12O6 and the formula of fructose is also C6H12O6. So, in this case, we can say the sucrose is a disaccharide, whereas glucose and fructose, they are monosaccharides, because sucrose is a disaccharide because on hydrolysis we got 2 monosaccharides, that is glucose and fructose. Okay. Now, here we have both the monosaccharides different. One is glucose and one is fructose. Now, another example for a disaccharide is maltose. Second example is maltose. Maltose on hydrolysis, we get 2 molecules of glucose. So, maltose, the formula is C12H22O11, same formula but different structures. H3O plus, that is on hydrolysis we get 2 molecules of glucose, C6H12O6. Okay, but in the case of sucrose hydrolysis, you cannot write 2 molecules of C6H12O6 because although they have same molecular formula, glucose and fructose, they have different structures. So you have to write C6H12O6 plus C6H12O6 and write the name glucose and fructose under the molecular formula. But here you can write it as 2 molecules because it is same, that is glucose molecule is produced as a result of hydrolysis of maltose. So these are the 2 examples for disaccharides, that is sucrose and maltose. Now the next type of carbohydrate is polysaccharides. So the third type is polysaccharides. Now polysaccharide means carbohydrates which yield a large number of monosaccharide units on hydrolysis are called polysaccharides. And example for polysaccharide is starch, cellulose, glycogen, gums, etc. Then these polysaccharides, they are not sweet in taste, hence they are also called non-sugars. They are not sweet in taste. And for example, starch formula is C6H10O5 N times. This is starch. Starch on hydrolysis, that is when it is treated with N molecules of water, we get N molecules of glucose as the product. This is glucose. N molecules means we know it's a polysaccharide. So starch on hydrolysis we get glucose as the product, and starch is a polysaccharide because it gives large number of monosaccharide units on hydrolysis. Now next we have a term called reducing and non-reducing carbohydrates. So these are the 3 classification of carbohydrate based on hydrolysis. Now next we have another classification, that is reducing and non-reducing carbohydrate. Reducing sugar or reducing carbohydrate and non-reducing carbohydrate. This is another classification. Now what do you mean by reducing and non-reducing carbohydrate? In reducing carbohydrate we have free functional group present, means I told you the functional group can be aldehyde or ketone. So the aldehyde or ketone group is free, means it is not bonded to any other atom or groups. It doesn't have a closed structure. Okay, so here the aldehyde or ketone group is free aldehyde or ketone functional group. Now non-reducing carbohydrate has no free functional group, which means the aldehyde or ketone groups are bonded. So no free functional groups. Now also, since there is a free aldehyde or ketone group in reducing carbohydrate, they give test with Tollens and Fehling's, or they can reduce Tollens and Fehling's solution. So here reducing carbohydrates can reduce Tollens and Fehling's solution, whereas non-reducing carbohydrate does not give test or cannot reduce Tollens and Fehling's solution. So these are the differences between reducing and non-reducing carbohydrate. And an example for reducing carbohydrate is, example is sucrose is a reducing carbohydrate. Okay, and reducing carbohydrate example is glucose and maltose, they are reducing. And non-reducing carbohydrate example is sucrose. So these are the examples for reducing and non-reducing carbohydrates. Now next we are going to study in detail about the monosaccharides. So next, monosaccharides again we are going to see. And under monosaccharides, we are going to study about glucose and fructose, the structure. and the reactions of glucose and fructose. Now, monosaccharides means the carbohydrates which do not further undergo hydrolysis. They are known as monosaccharides. Example, glucose, fructose are monosaccharides. Now, monosaccharides can be further classified on the basis of number of carbon atoms and the functional group present in them. For example, if the number of carbon atoms is 3 and the functional group, if it is aldehyde, then we can call this monosaccharide as aldotriose. And if it is a ketone group present, we can call it as ketotriose. Now, if the number of carbon atom is 4 and if the functional group is aldehyde, then we can call it as aldotetrose. And ketone is the functional group, it is called ketotetrose. Now, aldopentose. When you see this word, you can see that aldo means aldehyde functional group and pentose means there are 5 carbon atoms in that carbohydrate. Now, the next is, if it's a keto group, then we have ketopentose. Now, next, if there are 6 carbon atoms in the carbohydrate and if the functional group is aldehyde, then we can call it as aldohexose. And you know, our glucose and fructose has 6 carbon atom, and so it is, the aldehyde is a functional group in glucose, so aldohexose. And if it is a keto group, then we have ketohexose, and fructose is ketohexose. Okay, so this is another classification of monosaccharides depending upon the number of carbon atoms and the functional group present in it. Now, next we are going to study in detail about glucose, the preparation and the reactions, the structure of glucose, etc. So, let's see about glucose. Glucose is a monosacharide. Now, glucose, we know the molecular formula is C6H12O6. And glucose occurs freely in nature as well as in combined form. It's present in sweet fruits and honey. Ripe grapes also contain glucose in large amount. Now, let's see the preparation of glucose. First method is from sucrose. Sucrose is cane sugar. Now, sucrose, we know, we discussed it already. Sucrose is a disaccharide, and sucrose, on hydrolysis we get glucose and fructose. So, how will you prepare glucose from sucrose? Sucrose, when boiled with dilute hydrochloric acid or sulfuric acid in alcoholic solution, glucose and fructose are obtained in equal amount. And the equation is, sucrose is C12H22O11. This is sucrose. On hydrolysis, in presence of acid H plus, you get glucose plus fructose. Always write the names glucose and fructose under the molecular formula. So, this is the preparation of glucose from sucrose. Now, the second method is from starch. How will you prepare glucose from starch? And starch is a polysaccharide, and hydrolysis of starch will give glucose, N molecules of glucose. So, the equation is C6H10O5N times plus NH2O in presence of H plus, there is sulfuric acid at 393 Kelvin and 2 to 3 atmospheric pressure, we get N molecules of glucose. This is glucose. Okay, so these are the two methods, and from starch is the commercial method for the preparation of glucose from starch. Now, next let us discuss the structure of glucose. So, only two methods for the preparation. Now, next, structure of glucose. Structure of glucose. Now, the structure of glucose, we have a structure that is called the open chain structure for glucose, and the structure is this: CHO, CHOH 4 times CH2OH. This is the open structure of glucose. Okay, now the glucose was given this structure on the basis of the following reactions. So many reactions were done and glucose is given this structure. And if you look at the structure, you can see there is an aldehyde group, there is an alcohol group also. Now the CHOH is a secondary alcohol group and CH2OH is a primary alcohol group. So total 5 alcohol group and 1 aldehyde group is present in glucose, and you can see they are all in a straight chain. So the reactions that proved the presence of this structure for glucose that we are going to discuss. So the first thing is the molecular formula of glucose was found to be C6H12O6. Now the reaction, the first reaction is reaction with hydrogen iodide. Now when glucose was strongly heated with hydrogen iodide, it formed normal hexane. Normal means straight chain. Normal hexane, suggesting that all 6 carbon atoms in glucose are linked in a straight chain. So there is no branches in the structure of glucose. All the carbon atoms are linked in a straight chain. And the equation is, you will write the structure of glucose, CHOH 4 times CH2OH plus hydrogen iodide. On heating, we got normal hexane. Normal hexane structure formula is CH3, 6 carbon atoms, 1, 2, 3, 4, 5, 6. This is normal hexane. So this reaction proved that there is no branches. That is, all the 6 carbon atoms in glucose are linked by a straight chain. Now the next reaction, that is reaction number B, is glucose reacts with hydroxylamine. With hydroxylamine. You know the formula of hydroxylamine, it is NH2OH. It reacts with hydroxylamine to form an oxime. And it adds a molecule of hydrogen cyanide. So there are 2 reactions in B. It reacts with hydrogen cyanide to form cyanohydrine. These reactions you have learned in the chapter aldehydes and ketones. To form cyanohydrine as the product. So what does these reactions confirm? These reactions confirm the presence of a carbonyl group in glucose. Carbonyl group means C double bond O. So the presence of C double bond O group is confirmed by these reactions. That is, glucose reacted with hydroxylamine to give the product as oxime, and it reacted with hydrogen cyanide to give cyanohydrine. These are the reactions given by carbonyl group, means both aldehyde as well as ketone gives these reactions. So let's write the reaction. There is glucose. Glucose is CHO, CHOH 4 times CH2OH. When treated with hydroxylamine, NH2OH, you know water molecule is lost and we get CH double bond NOH. This H2 and oxygen is removed and we get the double bond does not break, CH double bond NOH. Double bond comes from C double bond O. Now here there is no change, CHOH 4 times and CH2OH. This is our oxime. Now the reaction of glucose with hydrogen cyanide. So again CHO, CHOH 4 times CH2OH plus hydrogen cyanide. Now hydrogen cyanide is formed, added to CHO after breaking C double bond O. So how will you write the product? CH, CnOH. Then the rest all same, CHOH 4 times, CH2OH. Here the C double bond O breaks and we get hydrogen cyanide added to C double bond O, and we get cyanohydrin as the product. So these are the two reactions that prove the presence of a carbonyl group in glucose. Now the third reaction is C. The third reaction is glucose on oxidation gets oxidized to gluconic acid, that is with mild oxidizing agent like bromine water. So with bromine water, it's a mild oxidizing agent, we got gluconic acid as the product. Gluconic acid means that CHO gets oxidized to COOH, and this indicates that the carbonyl group present is an aldehyde group, because this aldehyde group, even with mild oxidizing agent, they get oxidized, whereas keto group, they require strong oxidizing agents for oxidation. So this reaction proved that the carbonyl group present in glucose is aldehyde. So I am going to write the reaction, that is CHO, glucose, CHOH 4 times, CH2OH with bromine water, Br2H2O. CHO changes to COOH, it gets oxidized to COOH. The rest all remains the same. And this is the structure of gluconic acid. Now, the next reaction is D. So, we got that glucose has a aldehyde group present in it. Now, next is acetylation of glucose with acetic anhydride. So, the reaction is with acetic anhydride. Acetic anhydride formula is CH3CO twice O. Reaction of glucose with acetic anhydride gives glucose pentaacetate. Glucose pentaacetate, which confirms the presence of 5 OH groups in glucose. So, we know that when we write the structure, there are 5 OH groups. So, this reaction proves the presence of 5 OH group in glucose. Since it exists as a stable compound, the 5 OH group should be attached to different carbon atoms. So, I am going to write the equation of glucose with acetic anhydride. Glucose is CHO, CHOH 4 times, CH2OH with acetic anhydride, that is CH3CO twice O. Now, you can see there is no change for CHO. Now, CHOH will become CHO, COCH3 4 times. That is, the hydrogen of CHOH gets replaced with acyl group or acetyl group, that is COCH3. Now, in CH2OH also, that CH2O, hydrogen gets replaced by COCH3. So, this is glucose pentaacetate. Okay, so this reaction proved the presence of 5 hydroxyl groups in glucose. Now, the last is E, the last reaction. On oxidation with nitric acid is a strong oxidizing agent. Glucose as well as gluconic acid both yield a dicarboxylic acid, that is saccharic acid. So, the reaction is with nitric acid, we get saccharic acid. Glucose and gluconic acid. First glucose gets converted to gluconic acid will give saccharic acid. This indicates the presence of a primary alcohol group in glucose, because that CH2OH will get oxidized to COOH. Also CHO gets oxidized to COOH. So, primary alcohol getting oxidized to acid. Okay, with nitric acid. So, it shows the presence of primary alcohol group in glucose. So, how will we write the equation? CHO, CHOH 4 times CH2OH. On oxidation with nitric acid, you get the product as CHO will change to CHO remains as such, then CHOH 4 times, then COOH. Now I told you this is not saccharic acid. CHO also gets oxidized to COOH. Okay, so this is our saccharic acid. Both CHO and CH2OH. First actually CHO gets oxidized to COOH, we get gluconic acid. So if you write gluconic acid is COOH, CHOH 4 times CH2OH. This is gluconic acid which also gets oxidized on treatment with nitric acid to saccharic acid. So this is the last reaction which proved the presence of a primary alcohol group. You can see the CH2OH is also getting oxidized to COOH. So on oxidation with nitric acid, glucose as well as gluconic acid both gave a dicarboxylic acid called saccharic acid. It's a dicarboxylic acid, 2COH group, and indicates the presence of primary alcohol group in glucose. And finally, the exact structure is given by Fischer, and let's see the structure of glucose. That is the Fischer structure of glucose. Fischer structure of glucose. Fischer structure of glucose is CHO. Now, this is the first carbon, second, third, and here we have CH2OH. Now, this is our first carbon, second, third, fourth, 5 and 6th carbon, 6 carbon in glucose. Now, in second position we have HOH, fourth position HOH, fifth position also HOH. But in third position we have OH on left side and H on right side. So this is the Fischer structure of glucose. Okay, always number the carbon atoms, and third carbon we have OH on left side, whereas the second, 4 and 5 carbon we have hydrogen on left side. Now same way we can draw the structure of gluconic acid, and gluconic acid is COOH, then we have CH2OH here. Now this is 1, 2, 3, 4, 5, 6 carbon. Now second carbon we have HOH, fourth and fifth carbon also HOH, but on third carbon we have OH. Now this is the structure of gluconic acid. Now saccharic acid also we can have the structure. The saccharic acid is COOH. Let's number the carbon atom. 1, 2, 3, 4, 5, 6. Now let's write the hydrogen and OH. Hydrogen, OH, fourth and fifth carbon also we have hydrogen OH. Third carbon we have OH here and hydrogen on right side. So this is the structure of saccharic acid. So this is the Fischer structure of glucose, gluconic acid and saccharic acid, and these are the reactions that proved that the structure of glucose. So glucose has the functional group aldehyde in it. There are 5 hydroxyl group present in glucose, and there is a primary alcohol group, and we have CHOH 4 times. There is a secondary alcohol, 4 secondary alcohol groups also present in glucose. So, this is the Fischer structure of glucose. But the third carbon, we have OH group on left side and hydrogen on right side. And on the top we have, in the structure of glucose, we have aldehyde functional group, and at the bottom the primary alcohol group, CH2OH. Thank you.